Okay, I'm going to talk about integrated modeling in k.LAB. I will just provide information. k.LAB is like a modeling platform sought for scientists or people who want to just model and observe the world. And as such, I'm a really tiny bit, and I will give probably a more GIS, more related cut, whereas this is just the tip of an iceberg of a huge thing that is written about semantics, apologies, and I will provide a couple of links if you're interested in whatever is behind all this. So, what is k.LAB anyways? k.LAB stands for Knowledge Laboratory. It's actually, from a software point of view, a full stack for integrated modeling. So it supports the production, the curation, the linking, and finally the deployment of scientific artifacts. So the artifacts that could be data sets, but that could be also models by scientists, because if you have an NDVI that is a data set, but if you have an NDVI that is a model that calculates from other resources, the NDVI, as such, you could have water models and you could have results models. So depending on what the country, the government has available, k.LAB should be able to put together as a data flow, we'll see that later, and choose the right set. Let's start with what the pieces are. The first thing is the k engine, and that's the part that does the heavy lifting. So it's a server instance that collects everything from the k.LAB network, from this server you see, and puts together a data flow that harvests and with machine reasoning puts together the proper resources and models to return the observation that was requested. Then you have nodes. Nodes are those that actually represent the knowledge. You can put on nodes data sets, you can put on nodes models, and they will interact within the network with the engine and with the other components, so that when the data flow is actually generated, it will get whatever it can from the nodes, pulling the resources based on a weighting system and machine reasoning. Then there is a hub, because it is necessary that there is some instance that handles authentication, user generation, certificates to deliver certificates, and coordinates all the other servers. So as you can see, this is meant to be a distributed system. You can have various nodes. You can even decide to use this, have your own private node where you have your own models, your own knowledge, but still attached to the whole thing of the integrated network modeling, which I, in a second, explain what it is. And then we have two interfaces. The first one for scientists, it's the modeler. It's really integrated development environment, where you can model in a near natural language using concepts. And that's what I will show you today for most of the presentation, but you can do with this. And then there is the Explorer, which is meant to be for just end users, where you have a map and you have a bar, and you can just insert request observations. This is a software stack, but how do we come to a platform? And that's the ARIES project. It stands for Artificial Intelligence for Environment and Sustainability. That is a platform that made out of the software stack environment that scientists can use. This means the ARIES project, ARIES also refers to a team of scientists led by Fernando Villa, which was the initializer of all this. So this ARIES team and project put together data sets. Look for example, Copernicus data sets. They put them inside the adapters in the various k-nodes. They develop models and put them inside. So, and mainly they created from the ontologies, they semantically rotated a worldview so that you could have a language with which to express your own modeling. A tiny bit of history. This all started in 2007, so it's quite a bit that it's around. The University of Vermont as a scientific project. It gathered, it attracted various fundings, In 2012, Professor Villa went to PC3, where the headquarters, let's say, of k.LAB in the ARIES resides. That's the Basque Centre of Climate Change. And the project itself had a big boom in the last years because the UN decided to base its platform for rapid and natural accounting on k.LAB in the ARIES. So they have to provide a statistical division of the UN provides a platform to all countries in the world to do rapid natural accounting. And this is based completely on k.LAB and the ARIES. Okay, a quick slide about how you can do it if you want to try k.LAB. So you can just get to that link. It will give you some information about your operating system, and you are able to create a certificate with which you can access the network. The whole software stack is completely open source. There's a GitHub, you find it on Getting Started, and you could install it yourself. But some components and the whole data you can exploit it by accessing via a certificate to the integrated modeling partnership. What you can download is a control center, a tiny bit of software like this, from which you can start your own local K engine. So you will, with your computer, but attached to the whole network, be able to do modeling. And from there, for example, you can do it with end user. It just opens it up, you see a bar, and from that particular bar, you can just enter what you want to observe. Think it as environmental or political. It could be really anything supported clearly, but you could model what's missing. So if you start running innovation, you propose it to the system, propose it to possible observation. And okay, a simple one, if you just type select elevation, it will generate the amount of elevation, which is the observation that comes from the data flow of the calculation of this of the query length. Okay, you can also add semantic operators. Semantic operators are those that transform concepts. So you could say distance to city, which is a subject, and once you run this, it will generate a data flow that observes in every pixel of the map the distance to the nearest city. And since the k.LAB project embraces heavily the fair concept, it really wants to do reproducible science. And you can, there are a couple of tiny tabs here, and if you click on one of the tabs with the tree, that was a bit early, I will talk about this in a second, sorry. This is just one example. I will show you something a bit more complex and then I will show you the data flow. Anyways, when you insert an observation, the data flow will pull models for sources, and any observation that is generated on the way will be shown below the main observation. At some point, if you're a scientist, you will get to the limit of what is Explorer, and there you would like probably to use the model. And here is where you see actually this language where you say, okay, model runoff, observing certain inputs which should be crop coefficient, minimum or maximum temperature, and stuff like that. So this is a very complex one, but we should have a look at some simpler examples. This example here, if my colleagues of ARIES see it, they will like hang me, because this is a GIS example. I mean, you can always force a system, right? And k.LAB should be something where you model real concepts. But in GIS, we usually do stuff where we just get the job done. And for example, I want elevation between 1000 and 2000. That's not really a concept of the world, right? That you can model. But still, you can say, okay, model me this concept, which I just give a name, observing the elevation by giving this information. And it will generate that. This is an extremely simple example, and if you click on that tab on top, it will show you the data flow. It will show you exactly what happens behind the scenes when you run this. This means elevation in a certain range, okay, you have, if you click on this, here, you will see the evaluation that you entered here. If you click on this, it will show you exactly where the data come from. Because when you add a resource to a node, you have to add proper metadata. Because at some point, for example, for the UN, this was extremely important, you are going to generate records automatically from the models. Because everything is perfectly coherent and semantically allocated, so you are able to generate tables and real end-user records. And that's why if you click on a resource, there will be a nice representation of the resource. Let's see another case. Here I try to do something more reasonable. Let's say we want to model what we think is a land cover for outdoor purposes. So far from the city and possibly not in the middle of the water. And here you can do something like this, model behavior outdoor of land cover, observing like the distance to the city in meters, and land cover type, so you have to define what you want to observe, and then you say, okay, it's unknown where the city distance is minor than 10,000, and where the land cover, and here you can use another set of attribute, where you say, and where land cover is water level. And this will result in something like this. If you then look at the data flow, it's a bit more complex, but it will show you exactly what it does. For the cities, it queries OpenStreetMap, and OpenStreetMap planet instance, and then computes the distance from the features, and you can click on every piece, and it will show you what's there. Land cover, for example, is a merged instance between ESA land cover and Korea land cover, because they share different parts of the world. And extremely important, the fact to have a known semantically annotated worldview is what makes it possible to harmonize data. If you click, this would be clicking on the land cover resource. The land cover resource in this case, I mean, ESA land cover and Korea land cover have a different coding of the land cover itself. So when we have the resources, we give the semantic annotation to each code, and they merge to the same meaning. Because it's not a this is another example, just another quick one. So if you want to model forest elevation, so you go to observe elevation and the land cover type, and you can just say, okay, show me just where the land cover, show me elevation just where the land cover is forest. And same here, you see where everything comes from. To make it even a bit more complex, but this is really more GIS doing, so it's forcing a bit the system. You can also add where the slope is and put even more conditions. You will have then a data flow that represents everything. It's just to show you what you can do. Usually this is used more to observe existing concepts, not really to do fine-grained stuff that usually engineers or technicians. One thing that I find extremely cool, you can also generate on the fly lookup tables. So you say, model the level of elevation, observe the elevation clearly, with a lookup, and you just throw down here a lookup table where you say, yeah, between 0 and 100, and everything that this IM stands for integrated modeling is part of the worldview, which is all the thing that goes down to ontology. And it will generate you a map where the elevation is classified by the lookup table in a very, very simple way. k.LAB supports also changing time, so we started adding a couple of hydrological models, one of which is INVEST, if you are into hydrological modeling. And this means you for the hydrological models, we needed weather data, and Copernicus is beautiful for that. So we created an adapter, and this means you can model the Copernicus adapter, the Copernicus resource as a weather process. You don't see it very well, but you can define steps in time, and it will do it over a time scale, and you can model Earth rainfall volume, or minimum atmospheric temperature, maximum atmospheric temperature, or temperature itself, which is the average. Because you have to think that this needs to work globally. What does that mean? That if you do this for a year and you want a result for every month, you will then be able to browse it. But what happens behind the hood? Because I mean, preparing this data, or maybe you have local web data, and they can get into the game. The reasoner will decide if your local data are of better quality. And if you do that, you need to aggregate them. So again, since it's semantically annotated, it knows what to do with rainfall. It will accumulate it over the month. And the temperature instead, it will average over the month. And put them together. So both in the spatial and in the temporal scale, things are harmonized in the proper way. Last word about the worldview, which looks kind of like this. So think of it, I've never been able to do something like this, but you have to define really to the very, very bottom, where you have to define what is a puncture. And this goes down then to the whole file of ontologies, which is why in the syntax, really, you have to follow coherently. You can't say, give me elevation in degrees, because it will go down, and ontology, the validation against the ontology will fail. So it will tell you, it will give you a syntax error and tell you, yeah, you can't express elevation in degrees. So it's extremely powerful. And what we did recently, since we wanted, for a project, we had to interact in a more GIS way, we made a client in Python, which is available on Pi. And this client is for now a small library, and we created an example in QGIS that seems to be the best option, where you can just put something into the scripting editor of QGIS. So, just to give you a couple of steps, you install it with just pip, and then you have a couple of k.LAB imports to do, and then you're ready for the fun stuff. So, think of this as that interface where we had a map with just a bar, okay? So, think you are in QGIS, you have your scripting editor open, and you have your map canvas showing a local street map of some kind. And then, this is a bit of PyQGIS scripting that I will show you interview with the part of the k.LAB library. So, you extract from the current map region the polygonal extent, you create a region, then you create a k.LAB client instance, and you can start to generate observables as a grid with a certain resolution and a position in time, and submit it to the client. Since these kind of observations could also take long, it doesn't give the result automatically. It's a synchronous concept. So you submit it, you have a ticket handler that will wait and hold for the result every now and then. But when it comes, this is a quick one, you will get the context. Context is what the map was. That was the spatial context, it has also a temporal component. But here we see it more for what we're looking at now as a spatial context. So that will be it. You won't see anything down here, but I hope the presentations will get online soon. So it's what we saw before. And once you have the spatial context, you can start adding observations. Let's say, observable create, like geography, elevation, mentioned at 0. You submit it to the concept, to the context now, and you will again get a ticket handler, and will do the observation, generate the engine will generate the data flow, and execute it, and return back the results, and then you have a way to export it. You know that the elevation will be a raster, so you can export to file like this, and you can then just load it automatically as a QGIS raster layer into the map. I wanted to show also, some of you made the PyQGIS workshop, so you know somewhat, but we didn't see the raster part. So these are steps where you can just get out of the raster layer